In this video, we're going to talk about the conjugate addition to alpha-beta unsaturated carbonyls. We did 1,2 and 1,4 addition with dienes several units ago, and there are connections to those reactions with the alpha-beta unsaturated carbonyls. So just as a refresher, diene is two double bonds that are conjugated. If we add something like HCl to a diene, we can get 1,2 or 1,4 addition. So 1,2 addition is where the two pieces that are added to carbons 1 and 2. 1,4 addition is when you get the addition to carbon 1 and carbon 4. And in that process, there's some resonance involved with an intermediate and your double bond does shift. We were able to control which product was the major product, whether we were using thermodynamic or kinetic conditions. With carbonyls, we've already seen nucleophilic addition reactions, and these are what are parallel to the 1,2 addition shown here. It's a little bit harder to see, especially depending on which nucleophilic addition you're looking at, but just as an example, the cyano addition is a 1,2 addition. We're adding the cyano group to the carbon and the hydrogen to the oxygen. So we can think of those as the 1,2 positions. Again, it's not always real clear that this is a 1,2 addition, but it does kind of classify in that category. If we want to think about 1,4, this is going to happen when we have the alpha-beta unsaturated carbonyl. So where does that alpha-beta nomenclature come from? So carbonyl, whether it's a ketone or an aldehyde, doesn't matter in most cases, but we're going to have a double bond that is again conjugated. I can draw resonance structures here, so this can shift. So this is why it's called conjugated. But the alpha and beta position, the carbon that's 1 away from the carbonyl, that's the alpha carbon, and then the carbon that's 2 away from the carbonyl is the beta position. So alpha beta addition in this location tells us we're going to be adding groups into those two spots. So the mechanisms for the 1,2 versus the 1,4. So 1,2, again, we've seen this. We have our carbonyl and our nucleophile, whatever it might be. It's going to directly add to that carbonyl, so we call this a direct addition. We get our tetrahedral intermediate. And again, depending on the conditions, the exact mechanism is going to vary, but this is the general process. And then we can protonate. So this general mechanism is a little bit more clear as to why it's 1,2. We add something in that 1,2 position. For 1,4 conjugate addition, again, we're going to have our carbonyl and the double bond. The nucleophile, whatever it might be, is going to attack at the 4 position or the beta position. That's going to cause those pi electrons to shift, and then the pi electrons in the carbonyl to shift up to the oxygen. So our intermediate here is again conjugated. We're going to have resonance structures, so we can show what those would look like. And having this resonance structure of the intermediate does help drive these reactions. This is an enolate ion. Once we're to this step, we can have acid of some kind protonate the alpha position. And you get your final product. So we're doing alpha beta addition. We're adding into those two spots. So let's talk a little bit more about the alpha beta unsaturated carbonyl itself. So as I mentioned, we do have the resonance structure, and we can actually draw one more that I didn't draw on the previous page. So we saw a resonance structure like this with our earlier carbonyl reactions that showed that this carbon here is our electrophile. And that carbon is still electrophilic with the alpha beta unsaturated carbonyl, but we have another option as well. So once we move these pi electrons over here, we find that that positive charge ends up out on the end. And so now we have a second location for an electrophilic site. And the question now is which one's going to be preferred. So with the alpha beta unsaturated carbonyl, that beta position, the one out here, is the preferred electrophilic site, because once the nucleophile adds there, we have resonance structures of the intermediate. Whereas if the nucleophile would attack on the carbonyl carbon location, we would not have those intermediate resonance structures. So to see that, if I have a nucleophile and it attacks out here at that beta position, I can draw resonance structures. And the more resonance structures that you can draw, the more stable an intermediate is, making it more likely to form. Whereas if we were to, like I said, make the nucleophile attack at the carbonyl carbon, the intermediate would not have any resonance structures and therefore is less stable. So this is why that beta position is more electrophilic than the carbonyl whenever you have the alpha beta unsaturated system. The combination of the resonance of the initial alpha beta unsaturated ketone as well as the resonance of the intermediate is what really drives this reaction. If I had just an alkene, so no carbonyl, and I had the same nucleophile, whatever it might be, it is not going to attack that that alkene in most cases, because that alkene is not what we call activated like it is with the carbonyl present and the corresponding resonance structures.